Last week, I traveled first to BOCA RATON to visit the lab and interview the staff at PPL, or Pro Pickle Labs, who run the paddle testing program for UPA-A. And then I traveled from there to Baltimore to attend the Media Day at USAP, where we saw their paddle testing lab at Element US Space and Defense and heard from their staff. It was a lot of information to take in, even for me, and I love this kind of highly technical stuff about paddle metrics. I got hours of video from both of these trips, so I want to start in this video with some highlights from both labs because I think it's important to look behind the curtains at both organizations, hear from their staff, and see what their methods are and ultimately how they're testing paddles. The new exit velocity testing, or PBCoR, will dominate the topic for this video, and I also have other content that I'll release separately over the next few weeks. I do want to thank the UPA-A, PPL, USAP, and Element US Space and Defense for allowing me to visit their labs and talk openly with their staff. It was an illuminating week for me, and hopefully this video will be the same for you. And this type of transparency is much needed at this critical time in pickleball when regulations need to be defined to prevent paddles from becoming too powerful and spoiling the sport. So I'm going to show some highlights from each trip in chronological order. So I started at BOCA RATON at the PPL lab for the UPA-A and ended in Baltimore at the Element lab for the USAP.
So typically the normal method for getting in paddles and everything, we have paddles that get sent to us typically on a rolling basis, and I'm gonna actually just grab a paddle to have in my hands. So basically what happens is we get paddles sent to us, and so one of the most important things is making sure all of our stuff is conditioned before we begin testing. So this room is kept to the ASTM of it's 72 for the temperature, and then we have a humidity control 50%. We bring all the paddles in here so that they come to condition. We have all of these cubbies kind of sorted with different labels for what tests are being run on these different paddles.
So how many paddles have you tested so far?
That's a great question, Matt.
200, 300.
Okay. Because we, as of right now, with the provisional and interim and all that kind of stuff, we've done mainly spin and deflection testing, and then we've done a lot of research regarding PBCoR.
Okay.
And run testing like that. We haven't started like the actual certification yet, so that will obviously, we'll have quite the influx of paddles coming in for that.
So you've done 200 or so paddles for deflection and spin. About how many have PBCoR been tested on?
Oh, let's see, how many total probably?
I mean, this can be closer to 100 or so. I mean,
oh, okay, so significant.
Yeah, many paddles because, right, as soon as you test one, you learn what needs to be done to really optimize the process, right? So it takes dozens of tests before we figure out, all right, this is the exact process, and then you go through that process with a variety of paddles from different constructions, different styles, different weights, sizes, all that stuff, and then really figure out, all right, what we thought was going to work does in fact work, or we need to tweak, and we go back, and so you go through the process iteratively and get to the point where we finally are able to write the standard, publish the standard on the website so that it's able to be executed by anybody.
Okay.
Here is our MOI machine here. So, and again, we already have a paddle in here to make it a little easier for you. But what this is doing, and Curtis, I don't know if you want to elaborate a little bit more on like the importance of like what this value itself is for the MOI calculation, the moment of inertia calculation.
So the moment of inertia is, for practical purposes, what you would consider the swing weight of the paddle, right? How much resistance or how hard it is to swing. And so this is important because the derivations for the PBCoR and a lot of the other metrics are based on the conservation of momentum. So you need to account for all of the static properties and dynamic properties of the paddles. And what we do is we pull it back to a certain degree, again, specified in the documents, let it swing, and it counts the time it takes for each period of oscillation to occur. And then we take that data, run it through the calculations, and it spits out our numbers.
So it takes into account swing weight, and you're also clamping at 5 centimeters above the butt cap, right? So that's part of the MOI as well?
Yeah, so it's arbitrary, the point in which you put this, right? The specifications in our process are very specific. We always do it the same way, but you take that data and you run it through what they call the parallel access theorem, and it's a simple way to we can calculate the moment of inertia about any location, right? So we can calculate it for what it would be in your hand holding it like this, or if you're choking up holding it like this, based on the center of rotation, right? So
it's supposed to approximate the fulcrum, basically.
Exactly. What it does really is it's less about what a player thinks. It's specifically designed to measure the moment of inertia so that we can then specifically apply that value to exactly how we hold the paddle in the test.
Okay.
Over here, so this is our performance cannon right over here, sorry. I can start first with just how we load the paddle, and here, it's just, we clamp it. It is not allowed to rotate out like this way. It's clamped fixed here at that 2-inch location, same as we do for MOI.
Okay.
But it is free to swing. So what you'll see in the impact, ball gets hit, it's free to swing, and whatever, it is not fixed here. It's not like rigidly fixed here.
Okay. So this is centered at 5 centimeters, the pivot point, right?
Yep.
Okay. And it's free to swing, and it catches over on that.
It just hits this, so it's not banging against this glass right there, yeah.
Typically, the ball will pass through, and we have these different sets of light gates that measure the speed of the ball passing through, and also then the speed of the ball passing back through after rebound. The reason for the angles is that it allows us to identify basically the arc of the ball, any sort of angle off hit, right? Because if, say, this paddle is tweaked and now the ball is coming up or is going down, that's problematic. You're not going to get a perfect rebound. Right? We're trying to maximize the performance and not trying to minimize any sort of uncertainty.
Gotcha. So when you clamp it, are you like using a spirit level to kind of get it vertical?
We have this level too, and we also have,
Yeah, so same stuff we use for angularity on the spin test.
And I can show you on there too, if you're wondering like this orientation too, I'll show you where that number changes on our interface.
So
you
so
can
that encoder at the bottom tells you where it is with respect to the angle. Okay, fantastic. So you align it so it's perfectly perpendicular to the ball coming at it, and then also it's leveled vertically. Okay. It comes, it's allowed to rotate freely. These laser gates or light gates, whatever they are, they collect data on inbound versus outbound speed, and also the angle at which the ball is returning and coming. Okay.
This is our air cannon, right? Air cannon encompasses many things in the space. Some people think of it as a potato gun, right? A potato gun is the most simple of all air cannons, where you've got compressed air or some sort of gas that explodes out and fires an object. There's no control of orientation of the ball when you're doing that. It's random. Oftentimes there's spin, sometimes there's not. It depends on lots of factors. The second advancement of that is what we would refer to as a sabot cannon. And that's a cannon that has a much longer chamber in which there's a carriage that holds the ball. And that carriage and ball travel down the cannon once you've shot the air behind it. And the ball continues on as the sabot reaches the end of the cannon. There's a hole that is sized so the ball passes through, but the sabot doesn't. That allows you to orient the ball and make sure you're impacting it specifically and with no rotation. That's what's been used historically in all certification testing for baseball and softball. Most recently, that has evolved into what we have here, which is referred to as a piston cannon. So the difference here now is that there's no sabot, and that upon release of the pressure here, the piston itself extends out, accelerates the ball, and pushes the ball. So now you've got no sabot, you actually end up with much tighter speed control. And so while both this type of cannon, the piston cannon, and a sabot cannon are both capable of doing this testing, this is more efficient and provides you better consistency as well.
So the ball sits on this little pedestal?
The ball sits in here. We orient it exactly where we want it.
Okay.
Piston comes out, carries through, and what you would see on the high-speed video is that ball is delivered perfectly with no rotation, and
And you have the balls marked with quadrants here. Why does that matter?
So we'll talk a little bit about the core testing, but the quadrants matter because what we see in the analysis of the ball is that the ball is very orientation dependent. The COR, or the bounciness of the ball, differs depending on whether you hit it here or here or here. And it's not just different, but it's also very consistent. So what we find is because you have those inherent inconsistencies that we can measure, we orient the ball, and then we account for those inefficiencies or those the differences in the actual protocol.
Gotcha. And then we'll talk in detail about it in the interview later, but can you briefly explain why you're using Vulcan balls with holes rather than the USAP standard of using a Franklin without any holes in it?
Yeah, so that was really one of the first things we looked at was life would be easier, right? The more you can simplify any sort of test, the faster it is, the more efficient, the easier it is, right? Everyone wants easy. But easy at the sake of accuracy or correctness isn't really the right direction. So we looked at balls without holes. You want to grab the ball without holes?
Yeah, the one without holes? Oh, yeah.
All right, so when we look at balls with holes versus balls without holes, you can get good measurements with either one, but what we found is that when you're actually analyzing the ball performance, the characteristics of a ball without holes is dramatically different with a ball that has holes. So what you see is that as you increase the impact speed, the ball without holes performs a certain way, and the ball with holes performs a different way.
Okay.
So it's not just that one is faster and one is slower and they follow the same trend. They actually follow different trends, which means that as you start reaching those higher impact speeds, what you're predicting with this ball, because it's a different trend than the ball without holes, is going to be predicting the wrong thing. Wrong might not be the right word, right? It's what is predicting is not consistent with what you would see in the real world, put it that way. So you can get good, consistent data with both balls, but the accuracy and what aligns with real world expectations is totally different depending on which ball you use.
So a holeless ball is going to provide data that's different from the way the ball actually plays in the game.
Correct.
Okay.
If the game was played with balls with no holes,
right.
That's what you're predicting.
Okay. Thank you for that.
So doing the ball study was a really important part of our procedure for getting, PBCoR to where it is. And so what we did is we in general just did a study, like Curtis was just saying, balls with holes, no holes. For both we did, and with Franklin balls too. So we just did kind of an assortment of study, came to the conclusion of what Curtis just said. But what we did with it is we used this cement plate, right, instead of using a paddle. So it takes away this, we're just doing the ball COR here. Mm-hmm. And so what you do is you line this up for the shot, and we are just firing the balls, and we're rotating the quadrants. We have a set number of balls that we're doing, and we're rotating the quadrants, and we're tracking the ball COR per quadrant. And so, and I'll show you how to we do all this stuff, physically getting it centered and all that. But yeah, to Curtis's points, it's important because we've noticed that the ball, we need to be paying attention to where we're hitting on the ball and which ball we're using, right?
Right.
And so throughout the ASTM, there's mentions of C ball, this correction factor for the ball. It's making our data still comparable, if that makes sense.
So when you're collecting the PBCoR values, it's looking for an efficiency factor of how fast the ball goes in, how fast it comes back out. That calculation inherently assumes that the thing you're impacting has the same characteristics all the time. Mm-hmm. If it doesn't, you need to, or you should, apply some sort of correction factor to account for whatever those variances are.
Okay.
So that's why we use the specifically.
So real simply, this plate is to calibrate the balls for each quadrant of the ball, so you know exactly what their average rebound is.
Yeah.
Exactly.
The study is also important too because you get a batch of, however, let's say you order 100 balls. There is, it also allows you to say, hey, this ball is just maybe it's manufacturing, whatever it is. We don't want to be using a ball that's potentially already out of round and characterizing paddles based on balls that should not be qualified in the first place. Let's impact it at, let's do the 5-inch location. I type in my 5-inch here, I select go, and now you see the paddles automatically moving to be in the position in which I want to hit it at.
Right.
So I'm going to let it do that. It'll stop. Great. Now I'm at that 5 location, and what you'll see is when I fire a shot, my output will give me impact location to verify I'm hitting where I want it to hit, and it will come out with that number, and I can show you after. So I will take a ball and I will say, okay, here's my ball code that I have written. Here's the quadrant I'm hitting it at. So I'm gonna take this ball, I'm gonna orient it the way that I want. I'm gonna mark in here how I orient it. Close it, you'll hear the system pressurize. So I'm just gonna count down because it can be a little shocking if you don't know. So 3, 2, 1, bam. And so, and what happens is my screen gives out a valid shot, and it says true because our angle was good on that rebound, our inbound velocity was good, our exit velocity was good. So it does all those checks and allows us to say, okay, great, true. One thing to note too, with this, with the PBCoR that we get, that's not accounting for the ball. So once we're able to, and the ball correction factor, I should say. So what we do is we get all this intake, we get our PBCoR value, and then we look at our ball data from that particular ball, and we apply that correction factor to get like the ultimate value of that PBCoR.
We only allow a certain number of impacts per ball, right? So we did a long study and we looked at what the core is of the ball through 10 hits, 20 hits, 50 hits, 100 hits, right? Many, many hits. And what we see is a degradation over time. The average value of the core of the balls doesn't actually change a whole lot. It decreases a little bit through time, but the variation, the noise in that data grows significantly through multiple hits, likely due to the out of round of the ball and the way it changes on the impact. So we actually cut a ball off and we say, what is it, every 48 impacts is the number of impacts that we allow on a ball before it gets retired.
Okay.
So that's what we do. Right? So we get essentially 8 hits is required in order to get the core values for the quadrants, which leaves 40 impacts per ball for actual core testing.
What are all the markings in the ball? That'd be interesting to know.
So we have, and there's also on our SOP, we have a diagram about just regarding all this right here, right? We have, this is how we're tracking which exact ball it is. So the study we were doing, and then we have the quadrants labeled, right? And then, so this is quadrant 1, 2, 3, and 4. And what we do here is that we mark dots on them so that, like, let's say I hit in quadrant 2, I can, if I have a Sharpie or something, in quadrant 2, okay, cool, I'm orienting it there. What I do is before I load the ball on here, I go, okay, cool, I'm hitting in quadrant 2, I'm going to mark that, and I'm going to do that so that every single time that ball gets shot, it's already marked. I'm not forgetting to mark it after I do it. It's like, that's kind of the process of it. And so then once you have 48 little dots all over your ball, specifically 12 in each quadrant, then that ball is therefore end of life, not usable for our PBCoR or spin or whatever studies that we're doing with it.
So the other specific note on the quadrants is they're oriented around what we refer to as the hemisphere of the ball, right?
There's like a seam right here.
Yeah, so it's either a parting line or a seam depending on how the ball is made. There's for sure a different performance of the ball, whether you're hitting the poles, which is 90 degrees to the equator, if you will. So the performance of the ball is different there versus on the equator. And so if we were to only impact on the poles, we'd only have 2 impact surfaces on the ball, go out around faster, we'd get half as many hits on a ball. And so in order to maximize each ball, rather than using the pole COR, we use the equator COR.
So equator is referring to where the seam goes around the ball.
The seam, yep,
Okay.
exactly.
All right, so what we have now, our pickle press, you've probably seen it, you've probably heard of it. This is what we use for our on-site testing.
So this is your deflection.
Yes, this is our deflection,
Okay.
yes. So what we do is we have this carriage right here. We have a 6-inch span that the paddle rests on.
All right, and then the paddle sits on that.
So the paddle sits on this, and we have this block back here. It measures, so this right here is 5 inches from the top, is where this compresses, and then we do 4 inches, and we do that on both sides of the paddle, both face A and face B.
Okay.
So we run all 4 of those tests on every single paddle that comes in. So this compresses down. It deflects a 1/16 of an inch.
Okay.
There's one test.
Okay.
So we do that at 5 inches from the top, 4 inches from the top on both sides.
So This is our durability cannon. We talked about the different cannons earlier and how we orient the ball over here very specifically. This is different in that so this is a fully automated cannon system. So what you have here, and you can see actually we're using balls right now with no holes because the intent of this is twofold. It's to rapidly impact a paddle many times at different locations to start to look at the break-in of a paddle, but it's also to look at the long-term durability and consistency of balls. So this is a less precise version of what we consider the performance cannon. This is the durability cannon. So again, it's fully automated. You've got a lifter system inside. The balls impact whether it's a flat wall or a paddle. There's probably a paddle in there right now. And the balls get dropped into the chamber, and when it's fully running, it knows where the balls are, and it drops one at a time into the cannon. It's oriented randomly. There is no quadrant by quadrant impact. It just drops in. It measures the speed of the impact and the rebound as well. So we get long-term tracking of COR. Again, it's not as precise, but across large data sets, the data is useful and helpful in some of the things we do. So we use this in a lot of different varieties. It's not a part of any sort of certification standard, but it's certainly useful not just for R&D, but for better understanding of the equipment as we try to optimize the test. So one of the differences in the setup for spin analysis versus the PBCoR analysis is that you can see the clamp is physically different. The reason for that is that this clamp system is rigid. It does not pivot.
What's the angle of the paddle in this?
So
30 degrees. But for the certification testing, it'll be 30 degrees.
30 degrees. All right.
Yes.
we're also able to move the x-axis in and out, right? So we can scan the face to, right, say you've got somebody who decided, hey, they're only testing it at the 5-inch location. I'm going to make the 5-inch location slippery and glossy and the rest of it with glue on it, right? Certainly account for things like that.
And then what is the inbound velocity for spin testing?
It is 40 miles an hour for spin test.
So let's shoot one. You can get the shot of it in real time, and then we'll just jump into the camera and show you how we reduce the data.
3, 2, 1. Yeah, so we start by like calling frame 1 right where it is no longer making contact with the paddle, right where it loses contact with it. I can zoom in so that's easier to see. And then for our certification, we go from frame 10 to frame 50. We just use the endpoints of the marker at the first frame or frame 10 and then to the end frame. And then that gives us the spin rate of that.
So basically rotated 90 degrees in how many frames?
5,000 frames per second.
But if you started from the beginning where you started counting.
Oh yeah, 50 frames,
Okay.
50 frames.
And we've got a redundant calculation in there. So we look at it across 50 frames, calculate it from 10 to 50 and also from 30 to 50, right? So like,
Yeah.
well, the intent is within the reason we throw out the first 10 is we want to make sure that there's no like odd ball oscillation or other things, right? You see in other sports, after an impact, you'll get ball oscillation, and so you don't want to use those frames because they're not really steady state, right? It's kind of an inconsistency. So we go to frame 10 as kind of when the ball has started its real rotation or unimpeded rotation, and then we look at 50 frames later and say, hey, there's your spin rate, but then we also look at it from frame 30 to 50 and make sure that that data matches the 10 to 50, right? Okay. So there's redundancies built in for just quality of data because there's it's an optical method as opposed to like an automated measurement. I mean, we're not necessarily, right? We're not holding a protractor to the screen measuring the angle. It's all built into the software. But because it's an optical based system, we do have the redundancy checks in there.
So this video we're watching, what does the math tell us that the RPM of the ball is?
So it's 31.8 revolutions per second, which is 1900 RPMs.
So you're getting 1900 RPMs just shooting a ball at a stationary paddle angled at 30 degrees.
Yes.
Wow. Okay, I never thought that you get that much RPM.
So what I wanted to show you here is how RPMs are affected by the incident angle and how we're impacting. So at 45 degrees, right, if you've got a paddle that's just going to straight plow through the ball, what's interesting is that all the paddles are almost exactly the same. They all are going to show about exactly the same spin rate, like within 100 RPM, right? Within some small tolerance, because at 45 degrees, almost all paddles are going to have what we call a non-slip condition. So whether there's grit, whether it's smooth, whatever it is, at 45 degrees, the spin rate on a paddle is almost always the same. What you see is that some paddles drop off slowly and some paddles drop off fast. And so as you start to increase that incident angle, the balls slide on the surface more or less. The amount that they slide changes the ability for them to generate speed. And so what we looked at, and we spent, again, a ton of time working through the analysis, looking at 20 degrees, 30 degrees, 40 degrees, 35, 25. When you get to 20, most paddles drop off and you get very few that stand out, right? So like this is, you get outlier paddles that are clearly higher in spin than others, but this is only like pulling out your extremes. So we set that threshold to be 30 because it's in an area where there's still a lot of spread, because also what happens, you go to 0, they converge again, right? Everything, this doesn't go up, but this falls, right? So they all become the same number again. So they start at the same, they spread, and then they come back together because at 0, right, they all slide.
Right.
So, but it becomes super interesting because that curve is characteristic of each individual paddle. They're all different, and we look at this range because that's where there's the biggest spread and difference between paddles.
This is located. We weigh each ball every time. Each ball has an ID number. Each ball we keep track of.
That was your homework assignment. Each ball is weighed right before he takes it off of there and puts it in the cannon. That is one of those sources of variation we would not accept. It's like, no, put a calibrated scale. This room is temperature and humidity controlled. Temperature alone is, remember this ball? I hate this ball. Temperature alone is a source of variation of this ball. We all know that one. So we've locked down temperature, we've locked down humidity, and we measure every ball. Who's got a camera going? See all those dots on the ball? We only use it 30 times, I forget the number, but it's limited because the ball has a fatigue life to it. It starts to degrade over time. That's a source of variation. It takes about 30 shots to map a ball, map a paddle. So you end up with about notionally 1 ball per paddle it gets consumed.
So we talked about inelasticity and hysteresis, right?
Yep.
So I take it to mean that you have measured these balls to understand what the lifetime and inelasticity of the course, the degradation of the
I wish I was that good. You know what I did?
what you did.
I said, what's baseball do? What's softball do? What kind of experience do we have? We've done similar testing to say, yeah, we're seeing similar decay in performance. We rotate it around, we do the best we can. Is it good for more than 30? Probably. We just want to make sure we're getting near off the shelf.
That seems like an easy thing to prove instead of just assuming 30, right?
We've got enough data that says the ball still has, I'll call it as new property.
Okay.
And we learn from softball and baseball that, yeah, you got to make sure the ball doesn't start to become a primary source of variation. It's bad enough, so we've tried to, again, eliminate control.
Yeah, so the test standard lays out the process for how to find, the hot spots of the paddle.
No, on the ball.
On the ball?
Yes.
No, it's random because originally when we were doing the development testing, we kept shooting it at the same spot and the ball started looking like pancakes. So
Yes, so you keep track of where you're.
it's just random each time. Each time every time you go through, you just pick a different spot. It's very
More important.
The fundamental of the test is that we're loading the air cannon, we're pressurizing it such that we can get 60 miles an hour. The light gates get inbound and outbound velocity of the ball. The other set of light gates get, is it coming in true? Is there any off-axis error in there so that we can disqualify that shot if it's more than plus or minus 5 degrees, I think is the exact number. But that's what's going on here. This clamp is a free swinging clamp and it lets it just swing away. It's back to the pendulum on the string. We try to minimize any loss in that clamp, but we do measure that R omega squared term that goes in there and letting it fly out of the way. There is no, it would have to be an infinite stiffness to hold the paddle. You have to just let it swing out of the way. And if we did hold it, we'd be holding it in a manner that's not aligned with the way it's used. This clamp and this boundary condition, if you will, is deliberately chosen such that you still get flex in the frame. It's not really just a diaphragm test of the paddle. Any stiffness in the yoke of the paddle, we will see in the response area.
How important is like the parallelism between the paddle face and the incoming ball?
It's very important. We want to make sure we come in normal. He went real quick and dirty. We may or may not get a valid data. That's what these two light gates are doing, is making sure it came in 0 plus or minus, I think, 5 degrees. And the rebound is 0 plus or minus 5 degrees. And then when we do it's even more important when we do the RPM test. We're going to lay it over 45. That's where it really gets important.
You're a little better.
And that's going to be this afternoon's discussion, or later this morning's discussion, is that we need to get all 3 axes of data with the cameras, because we need to see rotation this way, and rotation this way. If we don't have it perfect, and if you only got 1 camera, you're going to miss. You're not going to fully characterize all 3 axes. So for this, it's not so bad. We just got to go in and out on the axis of the camera, and we can get that with just those 2 light gates. That's one of the reasons we had to go to high-speed video, was to make sure we could get all 6 axes of translation and rotation captured. The RPM test is maybe a little more challenging here, but if once we're on the Canon, we get good high-speed video, we're fine. But you have to be very careful. Good question.
Are there any conditions that can cause you to pull the ball from testing, crack, deformation?
No dead stings, no dents, no dings. Just it has to go through a visual, and he grabs it, weighs it. Every ball is weighed right before the test and inspected to make sure there's.
Yeah, I don't think we've ever run into any cracking, or the only deformation was after, I mean, probably hundreds of shots on those balls when they were starting to flatten. So. And
then are you guys ready to go? Okay, he's slowly bringing it in.
It's homing. So one of the things it has to do, you measure the length of the paddle, and we can show you guys where we do that in the other room. But you measure the length of the paddle, so you enter it into the machine and it homes it, so you know exactly, okay, this shot's going to be at 5 inches from the end of the paddle, so you know exactly that you are at 5 inches.
So he will, to get a full suite of data, which is why this takes so long, is you have to map the face of the paddle. Just like you map the face of a golf club. Thank you for our friends at Callaway and Ping. Just like you have to map the face of a baseball bat that's not sitting there. But we track down the face of the paddle and look for, it's getting bigger, it's getting bigger, it's getting bigger. Oh, now it's getting slower. So we know that the peak is somewhere in there. We can get pretty close by eye, but as a manufacturer, this will be the next discussion we're going to have, much like our little whiteboard pictures we just did. Does my paddle have a really steep sweet spot, or is it across the entire face? That's your data. I'd suggest you look at it.
It is across the face.
Yeah, everybody's going to claim it's across the face of the paddle. But that's what we're looking for, and how flat that response is tells us we're only going half-inch increments. Okay? I'm just saying, we drew the line at every half inch. Now, with that data, the other thing is, I'm very passionate about this, we will not release anybody's data. We will only release one data point, and that's pass. We don't release fail, and we don't release your numbers. we give that data to the manufacturer, and that's their data. They can do with it what they want. If you want to get into the PBCoR marketing wars, that's your data. We will not give that out. And then the profile of that sweet spot is another thing. That's yours. How about it? So I think you're pulling it in.
Yeah, it's just about set.
So it's 30 reps on the ball, right?
Yep.
How did we get to 30?
We wanted to make sure we never got past a degradation profile. How long is it stable?
Right.
That's what we were looking for. It's well past 30. The baseball,
You guys ran tests.
we ran enough tests that we saw that there was, it takes like 100, it takes a lot of shots to start breaking one down. We just picked 30 because that's about how many shots we use for a paddle. We said one ball per paddle sound reasonable, that's where we're going. But it was nowhere near 30. They were, originally when we started this up, we only had a few balls. We didn't really say, okay, that's the ball. Let's just get the first lot in here, get things tested. It took a while for them to start breakdown. 30, we're very comfortable with that number. Just send.
Used for baseball?
Baseballs is a little different. You do it per ear, and I think, I don't know, what is it,
40?
One calibration shot per year.
Yes.
A baseball, they calibrate each ball, and you don't need to do that because get the ball be enough. Just a solid ball.
Yeah, we almost put one hole in this ball so that it's at least a thin-walled sphere that's not pressurized, but we drew the line there. I hate this ball.
But you didn't measure specifically the attenuation of properties of the ball itself. So we don't know, we don't have a data.
I don't have the profile for that, no.
The profile say at 30?
No.
We're well within.
Yeah.
Okay, all right, just checking. All right. So that's 30.
30 is, I'll call it, experience in the lab during all the development work that the first balls we had, I'll just say 100 shots on them. We had a lot of shots on them and they were still reasonable. We were getting clear, we were getting consistent data. Didn't have to start looking for sources of variation. We've set it at 30 right now. And that's about how many shots per paddle.
All right, well, it's ready. So it's pretty loud. So we have, for those of you guys with cameras, 2 hands. Yeah, you guys with cameras, if you want to use one hand, you can kind of wrap around. All right, here we go. Watch your ears. Go. And that was it. Then you do that.
Can I see that?
For 23 more good shots.
Now, this is the sabot that pushes this in. We got another serendipity when we developed this test, is that it's the slide that's sliding through the cannon. We're actually throwing a knuckleball. So when we went to work to develop the RPM test, we had that luxury of knowing the ball's essentially coming in with 0 RPM, and when we go to measure the RPM off the paddle, when we put it at an angle, we attribute all of that to the paddle. And it gives us a pretty good baseline that we're starting at 0. There's no influence from, for instance, if we were using a ball machine, it would come in with a ton of RPM. We wouldn't be able to characterize that off-axis RPM very well. It would just be another source of error.
So I know you're not using balls with holes, but there's still a seam around it, the equator, that's calling holes. Don't those act differently if you hit the ball on the hole versus the equator?
Good question. The short answer is no, because the seam is the seam in the mold. It's a roto-molded ball. So you get a mark off. It's not really like a welded seam where you get a nice big fat weld. So it's a really good question. That's why we went to a roto-molded ball. That's why we went to a roto-molded ball that was, the very last processing was drill holes. We said, delete drill holes. I want everything else to be exactly the same. So
It's all good. It pumps up pretty fast.
I think he goes random.
What was the question?
The ball's put in random.
Yeah.
Because that's only a mark off of the seam in the tool.
name, sorry.
Dana.
Dana, to Dana's point earlier, you know, if you're not tracking where the ball is, so we know if you put it in one spot that the ball deforms. If you don't put it in one spot, we know the ball still deforms just by simple polymer physics, but less, right? And ergo, you would have some amount of variability from that slight deformation, which would also give you not precisely a knuckleball that would show up in your RPM test, right? Therefore, your SOP would probably be improved by marking the spots by where it's shot.
Around every time.
Exactly, right?
The short answer to your question is yes.
Yeah.
Yeah. Can you do better? Yes. And remember the discussion, crawl, walk, run?
Yeah.
We're in the crawl, walk, run of this now.
Yeah. And so, like, the thing that's just jumping out at me, John, is that, like, we say we look at the clamping. It's like, okay, there's variability? Probably some that we're going to assume it's negligible. Okay, the life of the ball, like 30 seems pretty good, but we don't have specific data to support that. Does the ball warp? Yes, but we don't really measure where we hit it. To me, there's a lot of compound and variability, and in the field of statistics, that's well documented to be a larger error than you would expect from your system. Do you have a concern about that?
Always. The notion of continuous improvement is another one of my passions. Can we do better? Yes. Can we do better tomorrow than we did today? Yes. If we improve 1% per month, you'd be surprised at the impact you
cleared out everything.
And we're absolutely looking for, in the context of ID and eliminate all sources of variation, where are they? How can we improve?
We appreciate that.
Yep.
Okay, cool.
Yep. No argument.
Yep.
We are in day one.
Continual improvement.
Day one, absolutely. Okay, we're gonna shoot another one and get your cameras out. We'll go for another shot again. He's got the the Canon is calibrated and dialed right now for 60 miles an hour. We just keep shooting. We get referees off those light gates to make sure it was a good shot. And he's got a few other checks in there for momentum balances if it's out. 5%? What's your threshold?
Yeah, 5% for the momentum.
5%, I'll call it check on the data, that if it comes out 5% above on the MOI balance where we didn't balance, we'll say, oh, let's shoot that again.
All right, is everybody ready? Yes. All right, go ahead and watch your ears. Here goes.
Are you confident that 60 miles an hour inbound is the best way to measure PBCoR?
I think for a number of reasons, I think we've got a good, reasonable speed to mimic the ball to paddle reaction. Because as measured by and as witnessed by the deformation of the ball, we don't see, in pickleball, we did a lot of on-court measurement with the pros. Yeah, they hit me right in the belly with a radar gun. That's close enough. But to try to figure out what's a reasonable speed, and then we brought it in here. I think we can all agree that 60 miles an hour is in the right regime. And then we went 40, 50, 60, 70, 80, 90, 100, and we saw what was happening to the ball. We came back and said, we're going to take 60 as a good, stable speed to shoot at that doesn't destroy the balls. It gets the post-buckled behavior of the ball. We wanted to make sure it snaps through. I missed the slide. Give me that ball. I missed the slide that shows when the ball hits the paddle. In the deck, if you pull that paddle away, I think it's in your sheet, and you pull the ball away, it's not a circle. It's a ring where the ball has snapped through and then comes back. We wanted to, that's post-buckled behavior. It snaps through, the spring rate changes, and then it continues to compress. We wanted to make sure we still had that in the data, because that's real. And if you go too slow, you won't get that.
I had a question about that. Did you do that post-buckle test, or did you get the ring on a ball that has holes because there's no, because without holes, you create pressure and
that's why you get it. I almost put one hole in the ball for exactly that reason.
For that reason.
Yeah, we almost did, and it was like, stop. Okay, we're gonna lock that in right there.
Okay.
We didn't know if that would add variation or minimize variation. We just said, all right, we're done. Crawl, walk, run? Maybe, yeah, maybe. I'll do science projects on this one, and we're going to keep any questions. We kind of started backwards. This is really the marquee test of the media today, the media event today, to make sure you see the details here. The lab next door, we can go stick our head into. I don't think we need to spend a whole lot of time there, but you're going to see the pendulums for doing all the mass property testing, the scales that we use for doing the weights, the optical surface roughness gauge is in there. We can spend as much time as you want, but all of that is really the pre-work needed to get this test loaded to get, come on, I was setting you guys up. Good data, okay? We're ready, okay?
Clamp it down, set it on here. So this pivot point, like John said, is 2 inches, the same as the 2 inches from the end that it is over in that clamp. So the MOI is the same. And so what we do from here, you measure the period. We have these light gates. We swing it, it goes through the light gates, and it tells you the period, how long it took to swing through a full cycle. These are our CT and X-ray machines. That's the one where we X-ray all your guys' paddles that you send in, see what they look like on the inside. So the X-rays they both can. That's for a CT scan, which we offer, but for certification, we only do X-rays just to see what's inside, right? So this is just a cool part of our company. We do a lot of super cool stuff like rocket parts, you know, high-tech circuit boards, yeah.
We're looking for load pattern. Just we're looking for consistency and structure, and what kind of structure is it? The construction.
You're pulled up. You guys can look as you're going by, but this is just kind of what a CT scan of the paddle looks like. So you can see through all the different layers if you guys are interested.
The depth and breadth of the ability to characterize the paddle here, and we can then use it to compare. If there's field problems, we can compare it to what was certified.
Right.
It gives us a baseline.
You can see core crushing too.
All right, well, here's our Instron machine. They come and calibrate it once a year, like pretty much everything else. And here's our load cell, calibrated the same. And, you know, the deflection test, it just takes a specific
test. It's a pretty straightforward test. That each frame, this is everything. This is what you guys would need a drawing of in terms of what the support blocks look like. How far apart are we spanning? It's not something he sets up every time. It's that. We set it in, put the paddle on it. It's the L in the length of that 3-point bend test, and it's just one point. That test did us well for what I'll call the Gen 1 paddles. Gen 2s, where you started to get a lot of that structure and the boundary conditions were I'll call it first order. That test is missing all that because we artificially supported it inside the frame of the paddle. Now, when you go to Gen 3s, it gets even worse. And that drawing I drew on the whiteboard, where the center of the paddle, as measured by this, looks great.
So, John, let's go edge to edge.
They're right. Like, instead of throwing the baby out with the bathwater, just change the H.
We could have a really long discussion on that.
Let's have it.
It's relevant. You're saying just move the support over here?
No, go edge to edge.
Well, when we go edge to edge, now we got to bring consistent L in, and that brings.
Well, you map it out.
And do I have to take the edge guard off?
And you what?
I got to take the edge guard off.
I don't think so.
I don't think so either. Like, when we say go to the edge, we don't mean the absolute edge. We just mean an arbitrary edge where the very.
Oh, so you mean go? I'll call this. I'll say this is 10 inches. Go 9.9.
Big delta, right? Like, what would be representative?
You got to go out to make sure you're out past.
I would set it right over the bars, the edge guard, and I would make the edge guard part.
Yeah, but then it also may benefit from having multiple measurements at the edges, standard as we do here, right, and see the delta between
these widths get wonky on you. There's not enough consistency in that width that I will always land out there in that, I'll call it Gen, can I just call it the Gen 2 area, the Gen 3 area?
Yeah.
You got to make sure you're out in there.
Well, I would put it directly over.
And if it's a variable length, now it starts to get a little
Now
much
that you have
different test.
representation of the.
Can I just say, this test solved the problem at the time, the technology at the time. And as technology changes, now you have PBCoR tests to address that. Saying this is the end all of the test, it isn't. But at the time, it was what was available. We could all do it in our
Yeah.
in our
I'm not
factories.
talking about that. I'm talking about taking now this test to the field test, because now you have a lab test, and now you have.
That's a totally different discussion that I'd love to have with those guys right there, because Stafford is trying to help us. I'll choose my words, is trying to see if we can get a reasonable representation of what we're doing here courtside. Because you're right, can we take this test, and is it all about this, or do we have a different setup? If it's all about this, that's a really easy test to run. So can we then take this stiffness test as a means to, as a surrogate for PBCoR test courtside? We're absolutely looking at that. What can we do courtside? Because I cannot bring that cannon. I will not be able to bring the cannon for RPM. So is surface roughness and coefficient of friction still relevant? Absolutely, because of the courtside. We've got to get a bunch of data to get that correlation down. But this is, I'm going to jump ahead. This is the coefficient of friction test that we use along with surface roughness that's over there. You've all seen that. That can be done courtside instead of bringing the RPM test, but we need to get that correlation data. And then we need to get some test fixtures that can go on the road.
And so when it comes to plain old simple ball. So good morning, like John had introduced, I'm from Image Systems, and kind of explain how we go about trying to make good measurements on top spin, or that RPM measurement of the pickleball. But it turns out that measuring those translation and rotational components are not as easy as we hoped it would be. And so I've picked my favorite 4 pitfalls of scientific imaging. I wanted to put about a dozen of pitfalls in here, but I was told I have to keep the list short. So we'll stick to these 4, my favorite 4.
Yeah. This is an easy pitfall. If you're not using a high enough resolution camera, you're gonna think you got this.
Yeah.
And you're gonna underreport.
Sure.
Way underreport.
So we can characterize and we can properly attribute energy to translation and rotation, so we know that this is good science, and we can measure in all those different dimensions. And now we can repeat this test over and over again to get these preliminary results. Now in this particular instance, our standard error was pretty high. I'm not saying that this was necessarily a good result, but I can say that our RPM measurements are a high degree of confidence. I firmly believe that these are the right numbers. There's just a lot of variability in the test, and that gets fixed with fixturing. So there's easy fixes here. I'm not saying that it's critical. I'm just saying here are some numbers from the tests that we did. We also ran at a 45-degree angle, and we see that the standard error reduces significantly. So what we see is, yeah, there's ways to improve the test, but we know that we're measuring and we're doing it properly. At this point, you might be saying, isn't this just a little bit overkill? Isn't this a little overly complicated? Can't we just take one camera and look at the ball and see how it's rotating? And that seems like a pretty reasonable request. So we did that. So here we just have one single camera, and we're using the native software, which is the Phantom Camera Controller, or the PCC software, and we're using their rotation tracking analysis. In this particular instance, we got 1,376 RPM.
With one camera.
But the other result was 1,200. We're 12% off. I'm sorry, we're 15% off of results. And in this particular instance, it was an overestimation. We could have easily done this test again, and if you just change where you start your frame and where you end your frame, you can change these results to get pretty much any number you want. We got RPM measurements on the same test from 0 all the way up to 3,000.
We will end up implementing something similar to this, and if now we can visually go back to the lab, we will take this and not put it on a tripod, all sources of variation. It'll be fixed to the wall on a frame that's just looking with 2 different angles, 2 cameras, looking right down at the money shot where the impact zone is. We don't need to go back to it, but we saw the skid in the data, we saw the acceleration, and then as soon as it's off the paddle, it's decelerating. We still have to decide exactly which frames we're going to grab. We got to get through the impact and skid. We got to get enough data that, back to your aliasing, we're not averaging over too long of a zone because it'll essentially underreport, and we're not analyzing too soon or too late. That's kind of that last little parameter that we need to set, is which frames are we going to grab. We're just going to pick it and say that represents RPM, and we've corrected for rotation in all 3 axes. The ballistic axis, the rifling axis, isn't the one we're really too worried about. It's the top spin and the side spin. Go ahead, John.
Can you or anybody speak to the angle of the paddle? I saw a summary slide that showed 45 degrees, and it looked like the 45 degrees was more accurate than 30
Quite a bit more.
How do you explain that?
Because I think you're getting and if you looked at the data, you saw some more squiggles. That impact zone was, I'll call it more dominant in that you got more skid at 30.
Okay.
And it hit and it skid. It took a little while to get through that impact and skid and then into just the 3 axis of rotation. And it's the rotation we were looking for. It's really only the 2 of the 3 that are really important. Go ahead.
And following up on that, was it a similar train of thought when it came to the speed with which you're firing at this as opposed to?
Yeah, we slowed it down to 45 miles an hour to minimize that big skid through the face of the paddle. It's relevant, but we didn't want it to dominate. So we found that it's settled down as we slowed down a little bit in terms of accuracy and repeatability.
But I do want to just kind of keep it moving along. Do you guys, especially in the media, have any additional questions about specifically spin rate that we can address?
I have a 30,000 foot level.
Yes,
so
absolutely.
the money slide on here was, okay, how does one camera compare to 2 in terms of accuracy? What I heard, and somebody can verify this, please, is that with one camera, you can get a range of 0 to 3,000 RPM on the same hit. Right? So it's extremely inaccurate. Is that correct?
Well, I'm going to use the analogy of a radar gun and the pitcher. The radar gun is most accurate if the catcher has got the radar gun in his helmet. Okay? You're going to get 100 miles an hour. If I got the radar gun looking this way, I don't see any motion between the pitcher and the catcher. It's just, that's that notion of you have to, and radar guns will correct for that off axis, that cosine error. If I'm looking over here, I'm going to underreport a little bit if I was right here. So we're resolving that all back to all 3 axes. Golf is a great example. The golf monitors give you RPM and off axis because they've got to make sure they've corrected and they understand how much off axis error was in there and just correct for it. So that's what's going on.
Okay. So it's not just a little bit of variation between 1 and 2 cameras, or one camera in this new method.
We don't have 1 degree of axis motion. That's the problem. That's another way of trying to explain it. We've got to get all 3 axes in there to make sure we're not missing anything, because you can generate a lot of error. John.
So can you kind of explain a bit about the relationship between USAP and NTS, or now Element? Just how is that formulated? And specifically, who developed the PBCoR formula? And how is it specifically different from baseball? I know it was brought in from baseball, but how confident do you feel that the PBCoR formula is as relevant for pickleball as the BBCoR formula is for baseball?
It's the same formula. We didn't develop it. It's built into the hardware and software that's part of the test facility. We call it commercially available off-shelf technology. We're out making this shit up, excuse my French. the cannon doesn't know that there's not a baseball bat in there. It's just characterizing that collision. We're measuring all the exact same things. We've just adapted that whole ASTM standard, that whole equipment that's been developed, tried and true, and we just put a pickleball instead of a softball, corrected for mass properties, and then we put a pickleball paddle in there instead of a baseball bat, corrected for mass properties. But we're measuring all the same things. We just had to, it's just like it thinks it's a really small baseball bat with a really light ball.
So the formula is NTS.
We didn't touch them.
That's NTS's formula.
No, that's part of the ASTM standard. It's embedded into the hardware and software that's used, but we didn't develop and that's a good thing. We did not develop.
Is it the same for other sports like baseball? Is there a COR for golf also, and is it the same formula?
Certainly, I'm gonna say yes. Certainly for the baseball and softball, because it's sitting on the air cannon and the way they're gathering the data. And it's the same with respect to momentum balance. It's just the pendulum on a swing thing. Golf might be a little different because I'm not sure how they fixture it and whatnot. I'm not going to speak to golf, but for baseball and softball, all of that foundational confidence carried straight across. Cool.
So coming back to the thing we talked about earlier, because I feel like to me this is the most important part of all of this. Like cool, we've made all these new tests and they seem to be able to measure things a little bit better, but ultimately the last 2 years have shown core crushing, and that still happens in plenty of paddles. Like, what is going to happen to these paddles that make it into the market, and how much does it have to happen for the paddle to be pulled? Because I'm just thinking, even for amateurs now, amateurs probably have it the worst in these tournaments where, I mean, if someone wants to hit it with a lacrosse ball a million times and crush it so it hits harder, nothing's going to stop them. There's no test for them. And if these manufacturers can build something in, which I feel like we've seen a handful of times to heat up on purpose, what are you guys going to do to pull those, and how many like sirens have to go off before you guys go, oh yeah, we're going to look at that? Because a lot of times I think there's this skepticism that, oh, USAP is like either getting this from reviewers or other people, they're not catching it themselves. Like, I feel like we should never really have to catch this. Like, it should be caught beforehand, which kind of goes back to the whole degradation testing. Like, I feel like we added all this stuff, but I don't know if it actually solves the issue we already had with paddles breaking down and getting better.
Yeah.
Well, yeah, the first thing is we're trying to address a lot, right? And so this is on the front end. What you're bringing up, you've characterized a result that is arrived at in many different ways, right? And so the lacrosse ball, how do we stop that, right? And there were accusations last year. I mentioned earlier our, I think, very rapid response to capturing what was essentially a manufacturing issue, right? So, and we got different answers from each of the manufacturers in that space, right? This was in early 23. And in some cases, it was a raw material issue. The cores were too thick and they were getting pre-compressed, right? And so they were soft to begin with. In other cases, the manufacturer claimed that it was an adhesive problem. Right? So at the time, we didn't want to take a position that, okay, all thermoform paddles, forget it, right? So we addressed it directly. We only addressed it at the pro level, but I think there was a buyer beware. At that point, people understood that, okay, there are some issues, and the manufacturers addressed that. And so there was a comment earlier, and I appreciate that this was made by one of the manufacturers, that ensuring a paddle that does remain compliant throughout its life cycle is up to the manufacturer. It's not up to us, because there's only a certain amount of things that we can test, right? And as John mentioned earlier, whatever we land on, even if this, the manufacturers in the room could agree on a number, what is that? And does it reflect a short life cycle? They want to see some paddles churn, right? They want to see people buying new paddles every 6 months. Another manufacturer says, I want to create the most durable paddle out there. That's the premise behind some new ones that just came out recently. And so for them, the life cycle is going to be 1 million hits or whatever the numbers, right? And so there's so many variables. John, I think, addressed it very well earlier. I think the premise that it remains compliant to all requirements throughout its life cycle is an important one. How do we test it? And how do we pull certification on it? We've already done it. Now, the fact that we haven't published the reasoning behind pulling the certification, that's on us, and we're going to change that going forward. But we've already pulled certification from paddles that have exhibited a off-the-shelf a life cycle change, right, or a degrade to benefit issue, and it's a very visible one last year, but we didn't say why. And so, like I said, I think that's the transparency people are looking for from us, and it's cost us not telling the story. And so I think we're going to start to do that to the extent, we don't want to throw anybody under the bus or air dirty laundry, but I think the market does need to know that they should ask, what is the life cycle of this product? And I'm going to spend $250.
So just one follow-up on that quick. How, if a paddle starts not being compliant consistently, like how do you guys find that out, and then how much has to happen before you act on it?
We have many sources of information. To your credit and the paddle reviewers, we do listen, right? Manufacturers, many of them in the room, source paddles from the competitors and conduct their own testing. But we saw a lot of this over the last few years in surface roughness. Someone would say, hey man, I bought one of these and it's hyper rough. And I think we all know in the room that there's some issues upstream on suppliers giving paddles to manufacturers to submit for certification, and then we find something else on the market, right? And so that's where our market compliance program, we've captured quite a few of those. Again, we handle those without airing the dirty laundry. Typically what will happen is we'll screen. If it fails, the lab will test. If it fails, we bring in John, the expert, to walk them through a notice of escape. And if it can be contained and defined, if there's a limited population out there, we don't need to pull certification. If they can't put a finger on it, that's a problem, because then the whole population's suspect.
I have just an add-on to his thing, because I think it's important. The expectation is that the manufacturers will keep it in spec, or that they even want to keep it in spec, but I feel like there is a benefit to companies doing that. So if they have a paddle that will heat up, that is oftentimes a benefit because it's a selling point. So it's like, if the expectation is for them to keep it compliant, like I feel like a lot of people don't really want to do that because they'll sell more if it goes above that limit. So I think that's why it's important to know like what's going to happen and how long does it take to get that caught. Because if a company can sell it for 6 months before it gets caught to another manufacturer, they're sitting there going, we followed the rules the whole time. We just got beat up by these guys for 6 months because they didn't get caught quick enough. You know what I mean?
Well, we're talking about millions of dollars at stake.
Yes.
Because each release could, yield a lot of millions of dollars. And if somebody jumps on a release, that's a lot of paddles that one manufacturer will sell, but then we would all suffer, right? The ones that didn't. And that's essentially what we're talking about. Because if I release a paddle, let's just say at 35 and somebody at 43, and then they get reviews, oh man, this is the fastest legal paddle, and here I'm trying to comply to keep the sport fair, or whatever it is, but I'm losing sales to it. My next paddle, you can be damn sure, if it's 43 and it's going over throughout its life, that's where I'm going to be if you guys aren't doing anything about it. And I think rather than letting that to get to that point, we should try and nip that in the butt early. So we all know that there's some way, a method of controlling how fast the paddle
So
can be.
to your point, Rob, we're not doing, I won't say that we're not doing anything about it. I mean, again, we're doing field testing. We've pulled certification from paddles that have exhibited this in the past already. But there's not a one-size-fits-all way of doing it. And it may not be the way that you're prescribing or suggesting. There may be other methods of doing it. And so we're open to this, whether it's some type of stress test up front. John's talked about all the challenges with that already. We've covered that pretty well. We do considerable field testing where we do capture this courtside. We know what paddles are breaking down quickly, and we follow up specific or directly with those manufacturers to understand what the failure mode is, what the population is, and what the remediation will be for it as well.
Are there standards or protocols where the manufacturer, let's just say, or somebody knows that that's a fast paddle, do you guys have some way that we can communicate or formally send in a complaint to investigate that particular product?
Does it need to be formal? I mean, we've never.
Well, I don't know.
Yeah, I mean,
We've
it's
never
not
opportunity
patently
call, so-
inconsistent and unfair, right? So you're saying you're not going to measure over the course. You're not going to find that global maximum, okay? Unless you hear through the grapevines that somebody may be violating, of which you then come down on that manufacturer, of which you also told the manufacturers that they're not going to be challenged per that. And so now, whether they did it on purpose or not on purpose, now they have liability on their books over something you said that you wouldn't measure, but then heard through. Again, inconsistent and unfair is what that feels like to me.
By didn't measure, what makes you think we're not measuring? We're not doing it up front. We are doing it after.
On the back end, right, exactly. And so like, if you do it up front, then you're transparent about it all the way, and then we can have some sort of measurement, and we can be consistent about what that global maximum is, how it's measured, et cetera.
As long as you acknowledge the challenges of identifying just what that is. Again, John talked about it earlier. Is it 1,500 hits? Well, then a manufacturer's going to design to 2,000, right? So there's almost an infinite number of variables that we have to factor in to make this work. I'm not saying we won't consider it if there's a logical way to do it.
So after hearing from the experts at both labs and both organizations, it's clear that they're using the most state-of-the-art equipment and they're on the right track with PBCoR and PEF. But there's also some concern that maybe they're not controlling every variable and whether or not these variables are compounding in a way that will throw off the measurements. We have two organizations using similar labs, but with different experts and different methods. And I think this is actually a good thing because having more than one voice of authority can help expose mistakes and inconsistencies more quickly and ultimately help us get to our goal of effective paddle regulation. So the difference in staff at each organization, I think, is interesting. Both the USAP and UPA-A have highly qualified engineers and technical staff running the labs, but overall the engineers at USAP and Element come from more of the aerospace industry, although the technicians at Element have been directly involved with baseball and softball bat testing. In contrast, the PPL lab, who services the UPA-A, has engineers with backgrounds in sports equipment testing who've been leading most equipment testing for baseball and softball at the two biggest centers for this at Washington State University and UMass Lowell. So it'll be interesting to see how things shake out at both labs considering the different backgrounds of their engineers. And I think it'll soon become apparent if both labs are getting the same results, and if not, then why. And understanding why is essential for accurate testing. Even though they're using mostly the same equipment and testing the same metrics, each lab is going about things in slightly different ways. For example, is the PPL's ball qualification procedure on regular balls with holes a better or worse method than Element's use of a ball without holes? Is Element's inbound ball velocity of 60 miles per hour better or worse than PPL's 50 miles per hour? Is testing ball spin more accurate with the paddle angled at 30 degrees or 45 degrees? Does the UPA-A have an accurate and repeatable way to measure a paddle's break-in, or is it too complicated as the USAP suggests? And lastly, are there alternative ways to measure a paddle's firepower that haven't even been tested yet, like edge-to-edge deflection? So as long as these labs and their associated agencies remain transparent, open to feedback, and keep inviting independent people in the paddle space to visit, then I think we'll soon have an answer.